In this lesson, we're talking about the law of conservation of energy. And the idea behind this law is that energy can neither be created nor destroyed. In a closed system, you can't get any new energy, so you can't end up with more energy than you started with, and you also can't lose energy. You can't end up with less energy than you started with total. This is similar to what we've seen with the law of conservation of momentum, in the same way that you can't end up with more or less momentum than you had at the beginning. So energy can be transformed from one type of energy to another. When we looked at momentum, we looked at transferring momentum from one object to another. In this case, the same object is going to keep all the energy, but it's going to change between potential energy and kinetic energy, as we'll see going into some examples. So this means if we look at a closed system, which is a situation that has no outside sources of energy, we're not putting more energy in, there's no explosions, no one's giving you a push, then the total amount of energy at the start, so the total at the start and the total at the end must be the same. Okay, so we've seen conservation before. This is not a totally new concept, but now we're going to deal with it in terms of energy. So it says both the kinetic energy and potential energy of a block freely sliding down a ramp are shown below, only at the bottom position in the sketch. We have both of them here at the bottom. Potential energy 0, kinetic energy 75. Fill in the missing values for the other positions. Well, my total, if I have 0 potential energy and 75 kinetic energy, my total energy is going to be 75. So at every single point on this ramp, the total still has to be 75. So if at the beginning my total needs to be 75 and I have 0 kinetic because I'm not moving yet, that must mean that all of that 75 is potential. And then as we start moving our way down the ramp, we get a third of the way down the ramp, a third of our energy has disappeared from potential because we're only at 2/3 of the height. And so that missing 25 joules has turned into kinetic energy of motion of the block. We go a little lower, and again, we lose another third of our height up the ramp. So we lose another third of our original energy. So we are left with only 25 joules. And those other 50 joules have now become kinetic energy. So we're moving even faster. And by the time we get to the bottom of the ramp and we have no height left, we have no potential energy left, it's all kinetic. So this is a good visualization. And again, we're talking about how high up the ramp we are in each case. That is going to determine our potential energy. And as we lose that height, then we lose that potential energy till we get to the bottom. But it's not just disappearing, it's turning into the kinetic energy of the motion as the block slides down the ramp. So, in words, the law of conservation of energy, or to shorten that, C of E, says the amount of energy a closed system has never changes. In other words, my stored energy initial plus my motion energy initial, that's a total energy, has to equal the stored energy final plus the motion energy final. And we can transfer between stored energy and motion energy, but the total has to stay the same. And with symbols, my stored energy is my potential energy initial, plus my motion energy is my kinetic energy initial. That has to be equal to stored energy final, potential energy final, plus motion energy, that's my kinetic energy final. So this looks kind of similar to what our law of conservation of momentum looks like. Again, we have initials on one side, we've got finals on the other side, and the two things have to be equal. The difference here is that we're talking about the same object having potential and kinetic energy at the beginning and at the end. And then it says under that, to be even more accurate, we can include energy lost to heat, and that is going to fit on the final side of things. So potential energy initial plus kinetic energy initial should equal potential energy final plus kinetic energy final plus energy lost to heat. Maybe I'll just write that as heat. So that might dissipate off into the air, but it's not like the energy just disappears. We know where it goes. It goes to become heat. So a good illustration of this is skateboard park on Phet. So here we are at the Energy Skate Park, and we've got our skater poised at the top of the ramp, ready to start going down as soon as we hit play. So here at the top of the ramp, my total energy is all potential. I don't have any kinetic energy because I'm not moving yet, and I'm at the top. So that's as much potential energy, that's as much energy as I can get. Now the way that I've got it set up right now, I have no friction, so I'm not going to be losing any energy to heat. And let's see what happens as we start going. So if you're watching the bar graph over here, we can see as she starts moving, the more and more kinetic energy that you get. That's a step through. So at the very top of the ramp, we've got no kinetic energy. She comes to a stop, all potential energy. As she starts coming back down the ramp again, she's picking up speed. Let's put this into slow motion. More and more kinetic energy till she gets to the bottom. Then she picks up potential energy as she goes back up again. Comes down the ramp. At any point we pause it, these two bars, put them together, will give us the total energy. You notice that none of the total energy is disappearing. So whatever place we pause, this little chunk will fit up here to give me the same total energy. At the very bottom, we've got very little, no potential energy if we're right on the ground, and it's all kinetic because we're moving the fastest that we can possibly get. So this is what your energy skate park looks like when we've got no friction, no energy lost to heat. Now if we put some friction in there, we won't put a ton, but some, put her back at the top of the ramp, hit play, very slowly we are getting more and more thermal energy. That's your heat energy. And actually we get more of that the faster we go, is where we get the most friction. So we can no longer get as high up the ramp anymore because some of our energy has gotten lost as thermal energy turned into heat. So we can't get as much potential energy. So now when we're looking at it, all three bars have to add together to give me the total. So the more and more that I get in thermal, the less that there is for kinetic and potential, and I can't get that energy back from thermal. So she goes lower and lower and lower and lower as we go. So we can start it all over again, bring her to the top, and hit play. So she doesn't get as high anymore because she's losing energy to heat, and she's also not going as fast anymore when we get to the bottom. And if we just let this play out, then she'll actually end up not going anywhere at all. I don't know how long this takes. We can take a look. So if you want to play around with the energy skate park yourself, I think I'm going to put a link in the lesson so you could take a look, see how it works, and watch how it goes. So back to the lesson. Another couple examples of potential and kinetic energy being conserved. So at the top, all is gravitational potential energy. As you let go, halfway down, we've lost half our potential energy, and we've gained it half as kinetic energy. And by the time you hit the ground, it's all kinetic energy. In the second example, they show the potential energy of the elevated ram of the pile driver. Pile drivers pound in these giant spikes into the ground, is converted into kinetic energy when we let go, when it's released. And that's what allows it to drive the spike into the ground. So, for example, a projectile is launched straight up into the air. If its initial velocity was 84.3 meters per second, so this is my V initial, how high does it go? That's going to be my height final, my final height. How high does it go? And it says use energy ignoring air friction. The reason that they give this specific instruction is because technically you could have done this question last year using kinematics, but that's not the approach we're going to take in this unit. We're going to use energy instead. So again, we're starting out with our potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. And as equations. So my potential energy initial is mgh initial. My mass and g are not going to change, so this is what makes me initial, is how high I start out. Kinetic energy initial is 1/2 mv initial squared. Potential energy final is mgh final. And kinetic energy final, 1/2 mv final squared. Now, any quantities that I know are 0 are going to allow me to cancel out terms in my equation. So a projectile is launched straight up into the air. We're going to assume it starts at ground level. If it starts at ground level, then h initial equals 0. So that's going to make this whole term just disappear, which is going to make my life easier. So it's shot straight up into the air. When it reaches its max height, hopefully you remember from kinematics from last year, my v final was equal to 0 at the max height. Otherwise, it would still be going upward. So that lets me cancel out this term right here, because v final is 0. And this essentially is pretty easy to now rearrange. I need to solve for h final. That's what I'm looking for. This is the term right here. So in order to get h final by itself now, I'm going to divide by m and g. And kind of handy, dividing by m lets m cancel out from here and here. G cancels out from the right side but not the left side. So this leaves me with 1/2 vi squared over g is going to equal h final. You could also make this vi squared over 2g if you like, to simplify it down. Either way, just be careful when you're typing things into your calculator. So I'm going to plug in my numbers. H final is 1/2. V initial is 84.3 squared. Divided by g is 9.8. And in the context of this question, we're treating g as 9.8, not a negative 9.8, because we're not talking about acceleration due to gravity. We're talking about potential energy. So I've got 0.5 times 84.3 squared. 84.3 squared divided by 9.8 gives me a final height, goes pretty high, 363 meters. That's 3 sig figs. 360 meters would be 2, also fine. So again, we start out by saying my potential energy initial, kinetic energy initial added together have to equal my total energy final, which is potential plus kinetic. And then we just start substituting in the equations for each of them. So part B asks me, if the projectile only reaches a height of 72 meters, so instead of 363 meters, it only goes H final being 72 meters, how much energy was lost to air friction? Was lost to air friction, on the way up? Or how much did air friction do how much work did air friction do slowing the object down? So because we can no longer ignore air friction, when we write out this first initial equation, PEI plus KEI equals PEF plus KEF, this is where my plus heat comes in. Air friction is going to have energy lost to heat, and I'm trying to solve for this quantity. So I can do all my substitutions again. This is still going to be mghi plus 1/2 mvi squared is equal to mghf plus 1/2 mvf squared plus heat. And I can cancel out all the same terms as I did last time because I'm still starting at ground level. So this H initial is 0, so this term is going to go away. I'm still going to come to a stop at the highest point, so my V final is 0, so that's still going to go away. And now I just need to solve for heat by subtracting this term to the other side. So I've got 1/2 mvi squared minus mghf is equal to heat. Start plugging in what we know. Heat is equal to 1/2 mass. This time we do need the mass of our projectile. We can't get away without a mass. So this is actually missing from the question, sorry. We're going to do a mass of 20 kilograms. So we'll get 1/2 times 20 times V initial squared, same V initial as before, so still the 84.3 squared minus the mass times 9.8 times our H final, which we were told in this question is 72. So type that into your calculator. And my calculator tells me that is 5695 2.9, which I'm going to round to 2 sig figs to 57, 1, 2, 3. Couldn't actually do 3 sig figs unless you use scientific notation, because this 5 is going to bump the 9 up to the 7 anyway. And this is measured in joules. This is how much energy lost to heat on the way up, or how much work did air friction do slowing the object down, 57,000 joules. Now, unfortunately on this handout, my A, B's, and C's for one question were often split over pages. Sorry about that. Hopefully you can flip over your page and still follow along. So part C says, what was the average force of air friction? Well, this is the work air friction did slowing the object down. So I know work equals force times distance, and the distance that it went was the total height, 72 meters. So to find the force, I'm just going to divide by distance. So divide out distance, and I've got force equals work over distance, and I know my work was 57,000 joules divided by the 72 meters. And I'm actually going to use this unrounded number on my calculator. So although I wrote 57,000, I'm actually using 5695 2.9 divided by 72. And this gives me an average force of 791 newtons. 790 would be 2 sig figs, would also be fine. So the next question you might ask yourself is, so when do I use conservation of energy? How do I know when that's the approach I need to apply? So this happens when there is a change in height and a change in speed, because the potential energy due to height is changed into the kinetic energy due to velocity, or vice versa. And especially we like to use this if there is a yucky curvy path that the object travels on. It doesn't necessarily go straight. And so that's what we're going to see in the next example. So a 72 kilogram skier is traveling at 18 meters per second. How high up the next slope can the skier reach? So he's going along, and we know as he goes up he's going to slow down until at the top he comes to a stop. So I'm going to start again with PI plus KEI is equal to PEF plus KEF. And PI is mghi plus 1/2 mvi squared equals mghf plus 1/2 mvf squared. Now we need to figure out if there are any terms that we can cancel. So at the beginning, we're definitely moving. Our V initial is not 0, but we're on the ground. We're at ground level, so I can cancel out my PEI. Goes up the hill, and again, at a max height, how high up the slope can he get? He's going to come to a stop, so I can cancel again this. VF is 0, so this second term here on the left side, right side will cancel. And then I am looking for height. So I'm trying to get this term by itself, and again, this is just like we did before, divide by mg, and it turns out the masses actually cancel. So I've got HF equals 1/2 VI squared over G. Plug in what we know, 1/2, my VI is 18 squared over 9.8. Plug that into your calculator, 0.5 times 18 squared over 9.8. Gives me a total height of 16.5 meters. Now notice this ignored whatever path we took. This was just our max height. So my ski slope could be kind of wiggly, weird, not going to be straight up. Definitely not going to be straight up, 16.5 meters. But that is the vertical distance you can reach, again, ignoring friction. So with friction, we would go a little bit lower, but it works as an estimate. Let's take another example. Example number 3, suppose it takes you an average force of 245 newtons to pull the bow back a distance of 68 centimeters. How much work is done pulling back the bow? This is a straight up work question. You can do this one. Try A and B on your own, then come back and take a look. So work equals force times distance. Force is 245 and distance 68 centimeters is 0.68 meters. Remember, you need to be working in base units. So that gives me a total work of 167 joules. 166.6, 3 sig figs. So how much potential energy is stored in the bow? Well, all that work that we did is the potential energy that is stored in the bow, 167 joules. So part C asks me, if the arrow has a mass of 42 grams, how fast should it leave the bow? In other words, all this potential energy at the beginning is going to be turned into kinetic energy of the arrow. So thinking conservation of energy, PEI plus KEI equals PEF plus KEF. And I might even start canceling terms this early if I can think of things like the arrow, when you pull it back, you're holding it, about ready to release it, is not moving, so KEI is going to be 0. It's not moving, no kinetic energy. And then all this stored energy is going to be released when I let go. It's not like I keep some of it for later, so all my PEF is going to disappear. Now this PEI is this work that I calculated at the beginning as the stored energy. So I might even turn this into the W. You could leave it as a PEI, just know that you need to plug in this number later. And KEF is 1/2 mVF squared. And I'm trying to solve for VF. So to move the 2 or the 1/2 to the other side, I'm going to multiply both sides by 2 so that the 1/2 and the 2 cancel out. And divide by m to get VF by itself. So what I'd have at this point is VF squared equals 2W over m, and square root that. Because we don't have direction given in the question, I'm not going to worry about a negative answer. I'm just going to take my velocity as being positive. I mean, in the direction he's shooting to the right anyway. So plug in what you know. Square root of 2 times 166.6 divided by the mass of 42 grams. Now we got to convert that into kilograms, which means divide by 1,000. So this is going to be 0.042. And plug that all in. So square root of 2 times 166.6 divided by the answer. And I'm told I'm going at 89.1 meters per second. So this same principle of storing energy and releasing it is what makes a Nerf dart gun work. So if you ever played with those, that's what's going on. Another example. A 2 kilogram model airplane flies horizontally at 22 meters per second. So essentially at the beginning, got my plane, is going at 22 meters per second. Put some back wings on there, I think there usually are. Straight horizontal. So calculate its kinetic energy. Well, we've done this before. KE equals 1/2 mv squared. We're not talking about any changes in height, so I don't need conservation of energy. I'm not changing the velocity, just straight up calculation. So 1/2 times 2 times 22 squared. If you want to save yourself some time, 1/2 and 2, they would actually cancel, and I'm just looking at 22 squared, which is going to be 484 joules. That says the plane goes into a power dive and levels off at 40.5 meters closer to the Earth. In other words, it's changed its height by 40.5 meters. It's lost 40.5 meters of height. So how much potential energy did it lose during the dive? Well, again, this is just a straight up calculate the potential energy. And it's going to be mg, and then I'm going to say this is going to be the change in height, how much height that it lost. But this is just essentially this 40.5 is how much did it change. So the change in potential energy, I guess we should say, would be mg times the change in height, because my mass and my gravity are not going to change. But I don't have the actual values of how high it started and then how high it ended. I just know that it's changed by 40.5, so I'm just going to plug that in. So m was 2. 9.8 is my G, and my H is 40.5. So plug that in. 2 times 9.8 times 40.5. And that tells me 793.8, which is going to round to 794 joules. So it lost that much potential energy. So next part asks how much kinetic energy did the plane gain during the dive? Well, if it lost this much potential energy, again, the law of conservation of energy says it has to go somewhere. And where does it go? Well, that potential energy goes into kinetic energy. So how much did it gain during the dive? It gained all the potential energy that it lost. So as kinetic energy, it gained this lost potential energy. So then what is its new kinetic energy? Well, it initially started with 484 joules, and it gained another 794 joules. So let's add those together. So 484 plus 794. Could do 793.8, but I'm going to end up rounding it. Oh, my calculator anyway. And so this gives me 3 sig figs is going to be 1280 joules total kinetic energy. And then neglecting, so this is going to be kinetic energy, you could call this kinetic energy final. This is essentially kinetic energy initial, if you like. Neglecting frictional effects, what is its new horizontal velocity? So I'm looking for new V final. So I know KEF equals 1/2 mvf squared. Solve that for VF is multiplied by 2 and divide by m square root. So VF is square root of 2 kinetic energy over mass, square root of 2 times this 1277.8. I'm going to use the unrounded version, divided by a mass of 2. Hey, look, they just cancel out. Isn't that kind of handy? That doesn't always happen. It's just because the mass happens to be 2. Then I'm going to square root that result. So I got 35.7 meters per second as my final velocity. So again, any changes in potential energy have to result in changes in kinetic energy unless you have heat going somewhere. Example number 5. Suppose the 320 kilogram roller coaster below is at rest at the top of the first hill. The top of the hill before it's about to go. It is given a very gentle push. In other words, we're not adding any energy with this push. We're just starting it rolling. So we're not increasing the energy. So this is saying V initial equals 0, but somehow it does start moving. So initial velocity 0 starts to roll. So here we are at the top of the hill. V initial is 0. And we want to know part A, how fast will it be going down here? Location A. So again, PI plus KEI equals PF plus KF. So if I'm not moving when I start out, that's going to mean I'm starting out with no kinetic energy, because kinetic energy is the energy of motion. And at level A, I'm at ground level, I'm going to end up with no potential energy. All of that 90 meters of potential energy has turned into kinetic energy. And I'm looking for V final, which is going to come from kinetic energy final. So let's do our substitution. So potential energy I know is mgh, so this is mgh initial. Kinetic energy is 1/2 mv squared, so this is my V final squared. And I'm trying to solve for V final squared, solve for V final. So to get rid of this half, I'm going to multiply both sides by 2 so that they cancel. I'm going to divide out the m, and they actually cancel on both sides of my equation, kind of handy. And I'm going to need to square root to get V final by itself. So V final is going to be the square root of 2GH initial. So pretty easy to plug those in. V final equals square root of 2 times 9.8 times 90. Square root of 2 times 9.8 times 90 tells me, ooh, look, nice even number, kind of handy. V final at the bottom of the hill is going to be 42 meters per second. No rounding necessary. Part B asks, how fast will it be going at location B? So I'm going to start out again with this idea of conservation of energy. PI plus KEI equals PEF plus KEF. And my final position is going to be up here. This is V final in the case of this one. For part A, this was V final down here, was what I was looking for. But I can choose whichever place I want to be or to be the initial conditions. So if I wanted my initial conditions to still be at the top of the first hill, that would work fine. If I wanted my new initial condition to be from A to B, would also work fine. Doesn't matter which one you're dealing with, you can choose. I'm gonna stick with, I think, this initial position, just because we've done it already, but you could choose this as your initial position and you would still get the same answer. So if this is my initial position, I am again going to cancel my KEI because I'm not moving to start with. But in this position, I now have potential energy. I'm not at the bottom of the hill anymore. I have potential energy, and assuming because I'm looking for V final, I also have kinetic energy, then I can't cancel any more terms. So I'm going to start putting in my formulas. So potential energy is mgh. This is going to be mgh initial. Potential energy final, okay, so that's mgh as well, but mgh final, and I do have a final height, plus 1/2 mv final squared. And I'm still trying to get v final by itself. So the first thing I'm going to need to do to get v final by itself is to subtract over this term to the other side. Subtract mgh final from both sides. So what I get then is mgh initial minus mgh final is equal to 1/2 mv final squared. To get v final by itself, again, I'm going to multiply by 2 and divide by m. So times 2 to this whole thing, and then divide by m to this whole thing. So these m's will cancel, half and the 2 will cancel, and on the left hand side, because I have an m in both terms in my numerator, I can actually cancel all the m's out. If only one of them has an m, and this will happen occasionally, then you cannot cancel the m's. But if every single term has an m, then it turns out you can. And square root that result to get v final by itself. So I've got square root of 2 gh initial minus gh final. Plug in my numbers. Square root of 2 times 9.8 times h initial 90 minus 9.8 times h final 50. Plug that into your calculator. And that gives me now a new v final of 28 meters per second. Also a nice rounded number. Now, if you had started with A being your initial condition, instead of canceling out your kinetic energy, you would have canceled out your potential energy, because at the bottom of the hill, my potential energy is 0, and used this 42 to calculate kinetic energy. It should give you the same answer either way you go. These are kind of fun. I don't know about you, but I'm enjoying myself. So let's see what part C says. It says at the top of the third hill, which is not shown in the picture, so we go to the top of B, we go back down again, we go up again. The roller coaster has a speed of 12 meters per second, so this is my V final now. How high is the third hill? So I'm looking for an H final is equal to what? And again, I can start with either set of initial conditions. I could even start with B as being my initial condition. The only reason that B is less convenient is that there's nothing going to cancel out here. Nothing's going to be 0. So just for the sake of it, I might start with A as my initial condition, but you could go back up here as also being your initial condition either way. But just because I can, I'm going to choose A to be my initial condition. So this is again PEI plus KEI equals PEF plus KEF. But now my third hill is going to be my final hill. So if I take this A as being my initial condition, that means that I don't have any potential energy at the beginning. I do have this 1/2 mv squared from this 42 meters. That's going to be my KEI, 1/2 mvi squared. And at the end, because it's asking me how high is the third hill, I must have potential energy. So this is mghf. And if it's telling me there's a speed, I definitely have kinetic energy. So this is 1/2 mvf squared. And this time around, I'm trying to solve for this h final. So I'm going to subtract this 1/2 mv squared to the other side. So 1/2 mvi squared minus 1/2 mvf squared. The whole thing can move over at once. That's equal to mghf. Then to get h by itself, I'm going to divide out the mg. So the mg on the right side cancels, and all the m's again cancel out of my equation on the left side. So I'm left with h final equals 1/2 vi squared minus 1/2 vf squared all over g. Plug in the information that we've got. 1/2 v initial was the 42 that I got in letter A. So this is 42 squared minus 1/2 v final is the 12 that I'm given in this part of the question divided by the 9.8. Let's see if I can type that into my calculator without making a mistake. 0.5 times 42 squared minus 0.5 times 12 squared. Put parentheses around the top part and divide all that by 9.8. And this tells me the height of the final hill is 82.7 meters high. So you can do some pretty nifty things with the conservation of energy, especially to do with hills and roller coasters. All right, that is it for this lesson on conservation of energy. So again, every single time we're going to start out with this equation. We'll add heat if they tell us anything to do with heat or friction, and then we start seeing if we can cancel things out, sub in your equations, and solve for what you're looking for. Good luck with your homework. There is another lesson before you'll get to the mastery check on conservation of energy. We're going to do some more practice. Have some more fun.